Unfortunately, we've lost yet another class due to a snow delay. I have no decision-making power there because if I did, we'd all be in the classroom. So we're going to take a look at finishing up graphing of our trig functions, namely cosecant and secant this morning. So starting with our cosecant function, we know that cosecant is the partner of sine. So cosecant of some angle theta is the same as 1 over the sine of theta. So we know, whoops, off the screen here, that we have that relationship, and that is the relationship that we are going to use to help us graph cosecant. So if we look here at the graph we're given, this dashed line here is, as you can see, y equals the sine of theta, or in this case, the sine of x. So if I were to trace over this function again here, just in this period here now, to start between 0 and 2 pi, we recognize that is our sine function, and I'll just continue it here. So now we have our sine function between negative 2 pi and 2 pi. This function here is our cosecant function. It's in blue. I will trace it over to make it even more dramatic a statement. So these things here, which look very much like parabolas, at least to my eye, this is our cosecant function. So let's take a look at some things that we see are going on here. I don't know about you, but one of the first things that catches my eye is the fact that we have here these vertical asymptotes. And it's taken too long here. Sorry for the dead air time. I should have done this before, maybe. But we can see here we have vertical asymptotes, and where we have these vertical asymptotes is whenever our sine function is 0, we have a vertical asymptote, which should make sense because cosecant is 1 over sine. So when our sine is 0, we have 1 over 0. So 1 over 0 is undefined, and that is going to be our vertical asymptote. So characteristic, whenever there's a 0 in the sine function, in our cosecant function, that gives us a vertical asymptote. Other thing that I am seeing is these parabola, these U shapes, occur when we have a max or a minimum in our sine function. So if I take a look at pi over 2, the sine of pi over 2 is 1. This 1, which is a maximum point for our sine function, is the minimum for this upward-facing parabola, if you will. At 3 pi over 2, this minimum that we have in our sine function of negative 1 is a maximum value in our cosecant function. So those are, I think, the two most important characteristics of our cosecant function. Well, actually 3. One is we absolutely need to see its partner sine function. Then we look for zeros in sine that become vertical asymptotes in cosecant. And any max or mins get flipped in our cosecant function. So before we move on to secant, let's take a look at some of the terminology that we've used before in this course. In terms of period, the period for our cosecant function is 2 over pi. This is the same as our sine function. We can see between 0 and 2 pi, we have a complete cycle. A complete cycle for cosecant is defined in terms of an upward facing shape, parabola if you will, and a downward facing parabola. So that constitutes a full cycle or period for cosecant. The other thing that we can see here is that this is also, like sine, an odd function, which means that there is symmetry with the origin. And again, we can see that from our graph here. Here's our origin, that this shape is flipped over the origin, and this here is flipped over the origin. So we have symmetry with the origin here, odd function. Now, in terms of our domain and range, the domain for sine is all real x's, negative infinity to positive infinity. For our cosecant function, the domain is going to be all real numbers except, and we have an exception because we have these vertical asymptotes, or these instances where our cosecant function is not defined and those values get kicked out of our domain. And those exceptions that are going to be excluded from our domain are going to be multiples of pi. If we look here at 0, which would be 0 pi, 1 pi, 2 pi, negative 2 pi, and so on, those are all values where we have a situation cosecant is undefined and we have a vertical asymptote. In terms of our range of this function, the range for sine was 1 to negative 1. We could see that here. We just fluctuate between 1 and negative 1. However, with our cosecant function, we can see that our range here, looking here, we start at 1, so our range would be starting at 1, and then we have a visit from the cat again this morning, which I heard was a star in the other videos, and then we go on to positive infinity. So the range is quite different because we go from 1 to infinity, so that 1 is a minimum, and we go to positive infinity. Then in these situations, our range here, and I'm going to show this with this union symbol, we start at, well, saying this backwards here, we really start at negative infinity and then increase to negative 1, or start, if you say it the other way, here's our maximum of negative 1, and then we decrease to negative infinity. So our range and domain are quite different from our sine function. So now let's take a look at the secant function here. And we know that the secant of some angle, I'm going to go back to thetas here. I like thetas better than x when I talk about angles. So secant is 1 over cosine theta. And again, if we look here at this picture, here is our cosine function that we know from all the hard work we've done both in our project and in our homework. So looking here between 0 and 2 pi, that would be a normal 2 pi 360-degree period for our cosine function. And comparable to what we saw when we looked at cosecant, our secant function looks like these parabolas. I'm just going to, well, because it continues on indefinitely. So here are our secant functions. Similar to what we saw in the world of cosecant, we have these vertical asymptotes, and now these vertical asymptotes occur when our cosine function is 0. So looking at this function here, this secant function, we see pi over 2. At pi over 2, we know that the cosine of pi over 2 is 0. And at 3 pi over 2, cosine is 0. So whenever our cosine function is a 0, an x-intercept, that gives us these vertical asymptotes in the world of secant, because when cosine is 0, 1 over 0 is undefined, and graphically that's represented by these vertical asymptotes. Similar to, and you know how I always say, look for the patterns, because the patterns will help make sense of math so often. So similar to the patterns that we saw with cosecant and sine, when we have a maximum value in our cosine function, that gives us a minimum value in our secant function. And when we have a minimum value in our cosine function, that gives us a maximum value in our secant function. So just like we did with sine and cosecant, let's take a look at period and symmetry and domain and range with this. So in regards to period again is going to be 2 pi. So the period of secant is the same as its partner function cosine. And looking between 0 and our 2 pi, we can see we have one complete parabola, if you will, going down. And if we put these two pieces together, we would have a complete parabola going up. Another way we could look at this that we might see it clearer, the full cycle, is if we look at this same 2 pi interval, but just split up a little bit differently, that we have one complete cycle up, cycle down. So the period is 2 pi. Now, similar to its cosine partner, this is an even function, which means that there is symmetry with the y-axis. And again, we can see this so clearly, I hope, in our graph, that if we were, well, I could take this paper and flip it over on itself, but if we were to fold this on the y-axis, this half would lie exactly over this half. You can see it here. This is the mirror image of that half there. Now, in regards to domain, where domain of cosine is negative infinity to positive infinity, the domain of this is going to be all real numbers, again, except, and we have to kick out of our domain, we have to exclude from our domain all those values, all those angles that are going to give rise to a vertical asymptote or an undefined situation. And that's going to happen at odd multiples of pi. Odd multiples of pi over 2. At all odd multiples of pi over 2. So let's take a look here. We have an undefined situation for secant at pi over 2. 1 is an odd number, 1 pi over 2. At 3 pi over 2, so 3 times pi over 2, another odd multiple. Here in negative territory, negative pi over 2 would be negative 1 times pi over 2, an odd number, negative, but it's still odd. And here, negative 3 pi over 2. So anytime we have an odd number that's being multiplied by pi over 2, that's going to give us one of these vertical asymptotes in our secant function. And now looking at range here, range is going to be the same as it was for cosecant. We're going to go from 1 to infinity, and then we are also going to have our range go from negative infinity to negative 1. So if we look here, we have a minimum value for our cosine function, which gives us this max for our secant. So we come from negative infinity, we hit a max of negative 1. For these, this maximum for cosine gives us a minimum for secant, so our range starts at 1 and goes to positive infinity. So here. So these are some key aspects of cosecant and secant graphs, and in the next video we'll take a look at an example for graphing.